I am Mr. Ish and I'm welcoming you to this video. Thank you for joining me. Here we are looking at second order differential equations. But when you are looking at this specific topic, it is imperative at the very beginning you learn how to recognize the two main types of second order differential equations before you start learning how to solve them. And the essence of this video is I'm going to show you how you recognize those two main types. If you are looking at this term d square y dx square and you see something like this, plus or minus y prime plus or minus y is equal to 0 or some other expression or variable or whatever it might be, think about what I have over here. You can rewrite it as this: plus and minus y prime plus and minus y is equal to 0 comma a. The only reason why I'm putting 0 comma a, it could be equal to anything, it could be equal to nothing, or it could be equal to something. Hence all of these can have coefficients. A second order differential equation must certainly have this component, and it may or may not have the first order derivative, or it may or may not have the y variable. So long as you're looking at this, you have a second order differential equation. It will have the second order derivative with respect to y, and perhaps the y variable and the first order derivative with respect to that y variable. Your two main types that you must understand and be able to distinguish are these: the linear and the non-linear. Now of course we're talking here about the linear second order differential equation and the non-linear second order differential equation. Of this, you want to be able to understand and recognize the homogeneous and of course the non-homogeneous. And over here we're not worrying about any types. You'll be able to recognize the homogeneous linear, the non-homogeneous linear, or if it's not one of these, you're looking at the non-linear. So what serves as the essential classification or the basis of this categorization? Think about everything in this form: d square y plus dx square plus, I'm just going to use pluses here, dy over dx plus y is equal to 0. You see how in all of these instances you can write an equation which is looking like this, is equal to 0. Don't worry about the fact that it's equal to 0 or something else for now. Your eyes should be focused in on this part. You're looking here at everything with respect to these variables which are clean. They're not affected, they're not influenced, they're not impacted in any way. What does that mean? You're looking at all of these derivatives of y and the y variable, which are all to the first power. That's what they have. Look at them. They all have the power of 1 to the power of 1 to the power of 1. They're not affected in any way in terms of another exponent. You're not seeing a root of this. You're not seeing a root of y prime or a root of y double prime. You don't want to be seeing these, because then you're no longer looking at linear. Also, you have none of these items which are in a product relationship with each other. You don't want to be seeing anything which is like y prime and y. You don't want to be seeing anything which is like y double prime and y. These are a no-go for linear. So the basis of the linear is this: you are looking at clean versions of these derivatives with respect to y or the y which are to the first power. When it equals a 0, you're looking at something which is homogeneous. When it does not equal 0 and it equals something else, then you're looking at a non-homogeneous linear equation. In all other instances, you're looking at a non-linear second order differential equation. What would be examples of those? Quick examples. These are instances where you're looking at something like e to the y prime. You see how these derivatives or your y variable are not in a clean manner. They're attached to something else by means of some sort of composite or by means of some sort of function. How about this sine of y? Here the y is not a standalone y, but it's attached to something. How about this cosine hyperbolic y prime? The y prime is inherently attached to something as a function or as a composite. It's affecting it in some way. What about this tan of y minus 1? Here your y is inherently attached as a function or it's a composite of something. These are not clean versions. And by clean, I'm talking about this. They're not clean or unaffected versions of your y variable or your derivatives of y. Therefore, they make equations non-linear. Anytime you have a linear equation, the equation is equal to 0, you have a homogeneous. If you have a linear second order differential equation and it is not equal to 0, then you have a non-homogeneous linear differential equation. Anytime you do not have this, you have that. The best way to understand these nuances is by me showing you a couple of examples and we can categorize them. Let's start with this equation. You're looking at a second order differential equation because you have this. You know y double prime is always equal to d square y divided by dx squared. That's your factor which distinguishes a second order from a first order from a third order differential equation right here. How would you classify this? You're looking at everything here either as being linear or you're looking at non-linear. And then if it's linear, you have to determine if it's homogeneous or non-homogeneous linear. Now, how do you go about doing that? Look at this. Well, what do you have over here? You have these variables or derivatives of y which are clean. They're attached to coefficients, which is fine. Here your coefficient is 1, here your coefficient is 8x, here the coefficient is 2, but they're clean, unaffected derivatives of variables of y to the power of 1. They're not affected in any way. So you're certainly looking here at a linear second order differential equation. If it's linear, now we can determine if it's homogeneous or non-homogeneous, H or NH. If it's equaling to 0, you're looking at a homogeneous differential equation. It's a linear homogeneous second order differential equation simply by means of these characteristics. Here's another one. We have a second order derivative with respect to y minus root y minus x is equal to 0. Is it linear or if it's non-linear? We have to determine that. You can rewrite it as this: y to the power of 1 or 2 is equal to x. Now you're seeing something here which is a y variable or a derivative of y. It could be either or, but it's not to the power of 1. So you know certainly by that you're looking at a non-linear. And it's not equal to a 0. When you took the x on the other side, it's not equal to 0. So therefore, it's certainly not a homogeneous. But you don't have to worry about homogeneous too much here, especially when you're looking at nonlinear. If it's nonlinear, it's certainly or most likely not going to be homogeneous. What we have over here is a nonlinear because of this specific factor over here. How about this? 2 multiplied by y double prime minus 4x y single prime minus xy is equal to 2x squared. You know these primes mean single prime means single order derivative, double order derivative with respect to y. Look at all of these instances. You have coefficients attached to the y, but the y stays as a power of 1. It's not affected in any way, so certainly you have here a linear second order differential equation, but it's not equal to 0. Therefore, you're looking here at a non-homogeneous linear. And that's exactly what you have, a non-homogeneous but linear second order differential equation. This is the factor which makes it non-homogeneous. These individual coefficients here keep it linear, so you're good. It's been classified non-homogeneous and linear second order differential equation. Let's look at this. Y double prime plus xy prime is equal to sine y. You have to classify this. Push this on the other side. You're looking at double order derivative with respect to y plus x times single order derivative with respect to y minus sine y is equal to 0. Well, it's equal to 0. You're not worrying too much about that because you have an item over here which kind of influences or corrupts your y variable. It's not a y variable which is unaffected or unadulterated. It is very much an influenced variable. It's affected by the sine function. So what you're looking here is a non-linear differential equation. If it's a non-linear, you don't have to worry about homogeneous or non-homogeneous. That really applies to only linear. Here you certainly have a non-linear, and this is a factor which makes it non-linear. Your y variable is very much part of another function, hence it's an affected y variable, making it non-linear. Let's look at this. 3y double prime plus y is equal to 2x cubed. How would you classify this? I'm looking at a y double prime second order derivative. I'm looking at a y variable. They're not affected or influenced in a way, and they look very much linear to me, and it is indeed a linear second order differential equation, but it's not equal to 0. Hence this makes it a non-homogeneous because it's equal to something other than a 0. It's equal to some sort of function. It's a non-homogeneous linear differential equation. This thing right here makes it non-homogeneous. These unaffected y variables or derivatives with respect to y make it linear, and that's your categorization for this example. Let's categorize this. We have sine x times y double prime minus cosine x times y single prime plus y is equal to 2 times y single prime plus 5. We have to categorize this. It would be prudent to push this on the other side. You have sine x, and then you have this double prime y, which is second order derivative, minus cosine x times y single order derivative minus 2y single order derivative with respect to y plus y is equal to 5. When you're looking at this right here, you can isolate, and look what happens. You have sine x with respect to this double order derivative of y minus cosine, and isolate this cosine x minus 2, and you're looking at it with respect to this y prime, and you would want to be bringing in a plus over here. Plus y is equal to 5. Now that we've done this, if you were to open this up, you should end up with that minus cosine x y prime minus 2y prime. That's exactly what we have. What do we have over here? We have coefficients with respect to y variables or derivatives with respect to y, but nothing is affecting or influencing that y, so it keeps it a linear. So this right here is a linear second order differential equation, but since it's not equal to 0, it's equal to something, it's non-homogeneous, and that would be the correct basis of this classification: non-homogeneous linear second order differential equation with respect to y, and our example has been solved for you. This here is our last example: 2x squared y double prime plus x y single prime is equal to 3x. These two are in a product relationship with each other, and that right there is the problem. Remember, I said at the very beginning the y variables or the derivatives with respect to y must not be in a product relationship, and they must not be affected in any way. They must maintain single power. Well, they do have exponents to the 1, but this right here, product relationship, spoils it, and it makes it non-linear. And you don't have to worry about homogeneous or non-homogeneous. Technically, you don't have something equal to 0, so it would be non-homogeneous, non-linear. But the more important classification is you have a non-linear second order differential equation with respect to your y variable, and that's certainly what you have. You could look at that same sentence in the following way: 2x squared, and then you're looking at d squared y divided by dx squared plus xy, and then you have dy over dx is equal to 3x. You see this right here? This fact right here is what makes it non-linear. You have a variable and a derivative with respect to y in a product relationship with each other, and therefore it's no longer linear, it's non-linear, and this right here would be your answer. And that's it for this video. Just keep in mind all the things I've told you. You have to be able to classify based on linear and non-linear, and then you would learn your differentiating techniques based on that. Thank you for watching. Have a good day.